So we said in the last video that electron transfer, when it's occurring through an outer sphere mechanism in between two transition metal complexes, has some barrier, and that barrier is due to just the coordination, um, uh, the first coordination and second coordination spheres, the atoms, within the ligands, and the solvent molecules around the complex, moving around and getting in position so that you have effective overlap between the orbitals so that electron tunneling can occur. And so, even saying something as simple as direct electron transfer occurs is actually, you can always dive deeper into things, which I guess that's the moral of all this. But we were really interested in looking at self-exchange reactions, right? Which were reactions in which all you're doing is having the same molecule doing electron transfer to itself. So having like an iron 2 and an iron 3 going to itself, same metal complex. And even for that case, you still have a barrier because you have to have this rearrangement that we talked about of the atoms. And so we could describe using the harmonic oscillator the energy profile of these complexes, okay? And they're going to be the same shape, okay, in a self-exchange reaction because it's the same molecules, but they're going to be the position of them is going to be different because, well, they're in different positions in space, right? And so the intersection of the parabolas therefore tells you, hey, this blue molecule, metal A, has to vibrate and move in a way, its atoms have to move in a way in order to get to this point, okay? And so that you can have electron transfer, then go and deliver it to metal B. That is the idea. So you can look at the self-exchange rates for different transition metal complexes, and you see something very interesting, which is that there are huge, just like ligand substitution reactions, huge variations in the rates. Look at this iron Bippy complex, a bipurity. It's two pyridines linked together, type of ligand. Very fast, okay? 3 times 10 to the 8 is the rate constant. But you look at this chromium 3+ to 2+ complex, very slow, 10 to the -5 is the rate constant. Why? Has to do with the change in bond length. For this chromium complex, you're going from a chromium 3+, right? Which chromium 3+, remember, we saw that if we look at the periodic table, chromium 3+ is a D3 metal because chromium is in group 6. So it's a D3 metal. It's a very inert complex. D3 metals have a high crystal field stabilization energy. And now you've reduced this to the chromium 2+, which now is putting an electron in the EG orbital. So that's really going to change your bonding. It's really going to change your bond lengths. You're going to go from pretty strong bonds in chromium 3+ to a lot weaker bonds in chromium 2+, because you put an electron in this anti-bonding orbital. So you have a bond length change, a metal ligand bond length of 20 picometers, which is relatively large between these two states. So that means the atoms have to move around a lot, okay, in order for electron transfer to occur. So this barrier is relatively high, and hence you have a slow rate, okay? And you can see for this iron Bippy complex, there's basically no measurable change in the bond length, and so it just blazes on through because you don't have to do much reorganization for electron transfer to occur. And so when you have self-exchange in Marcus theory, your graphs look like this. That's where your energies of reactants and products are the same. What we want to talk about now is what if your reactants, the two things reacting, your reactants and products are different, right? And so that would be like probably a spontaneous reaction we're talking about that has a positive voltage, or if we're talking, in terms of redox potential, positive voltage means, you might remember, delta G equals negative NFE, or which is E energy, which is V voltage. Okay, same thing there. So if you have, since there's a negative sign in that reaction, if you have a positive voltage, it's a spontaneous reaction, that means you have a negative delta G, and a negative delta G, a negative change in free energy is a spontaneous reaction. So that is going to be a case where your product is more stable in energy. So it's going to have less energy than your reactants. So what you can do is you can kind of do this interesting thought experiment where you think about, well, what if I have a greater voltage, greater driving force? So my product is even more favorable. You know, you can look these things up on the table standard reduction potentials and try to figure out what the driving force would be. Okay, and so then your product parabola is going to go down lower, and yeah, you know, your barrier is going to get lower. So your reaction is going to go faster. It makes sense. You're driving the reaction harder. So yes, of course, your reaction should go faster, right? This is the mind-blowing prediction of Marcus theory. The mind-blowing prediction is that if you increase your driving force even further, so you lower this barrier even more, you will actually have a slower rate. And this is borne out in experiments. And so in the next video, I'm going to dive deeper into this phenomenon. It's called the inverted region. It's totally counterintuitive, but extremely, extremely interesting and experimentally proven.